to another MRSEC seminar. Again, some simple ground rules. You're muted on your way in, but I encourage you to unmute yourself if you have a question. Just jump in. It will help make this a more dynamic experience for everyone and more comfortable. But if you don't want to ask a question live or with your own voice, you can type it into the chat and then I can read that for you. Of course, we'll have questions at the end. And that's about it. So I want to introduce Karen Whiney, who is coming to us from the Penn Material Science program in Philadelphia. But she has some history in Massachusetts. I guess she did her PhD in polymer physics at UMass, our friends to the west. And then before that, even further west in Cornell, she did her undergrad. And she's been very focused on polymer science in general that whole time, I guess, since her grad school work. She's been an editor for Macromolecules and chair of the Division of Polymer Physics in APS, and has been at Penn, I think, her entire career, following her postdoc and some other postgraduate work, yes. So today I think she's going to talk about the role of nanoparticles and polymers, and let's hear it, what she has to say. Welcome, Karen. Thanks.
Thank you, John. Thank you. So it's a real pleasure. And originally we were thinking I would be able to visit remotely in August, and then Kerflooey happened. And I really needed the extra time to put together this seminar because I haven't spoken about our nanocomposite work in long form in quite a few years. I've been very focused on ion-containing polymers and ion transport. And so it was really a pleasure to put all these pieces together. So you are seeing the maiden voyage. And as you would, it's not uncommon that the title that one gives initially is not the same as the title one comes up with the night before when they're actually finalizing the content. So I'm going to talk about polymer conformations and chain scale dynamics inside confinement, rigid wall confinement, and in polymer nanocomposites. I'm leaving out the segmental dynamics. It's just not that interesting. And so before I get too far into this, I just want to, hang on, I have to hide something so that I can, yes, okay, that's good. So I just want to make sure I do the acknowledgement. So we've worked in polymer nanocomposites for a very long time, and this group of students and postdoc actually have data and contribution inside this talk. There are even more who've actually worked in nanocomposites. My work with Russ Composto and Rob Riegelman, who are both at Penn, will be very evident as I go through the talk. We currently have a project with ExxonMobil that we're excited about. And what I really want to, my goal for the talk is that you hear something interesting and then you want to read more. And so that's my website there in that pink box. You can find our papers, our manuscripts there, and then have a more thorough read. So this is a little bit more of an advertising of the types of things we've done, some high-level conclusions, but there's a lot of meaty details in the papers. Okay. All right, so polymer nanocomposites are a very versatile class of materials, and they're basically polymers with nanoparticles. It's that simple. But in the polymers, you can pick different chemistries and different architectures and different molecular weights, and all of that's going to impact their properties and their dynamics. And nanoparticles, I mean, most of what I'm going to show you are spherical silica particles, but there's a huge variety of nanoparticles, from the silicates to carbon nanotubes to nanowires. And people use different types of nanoparticles to tune different sorts of properties, whether it's mechanical properties or optical or magnetic properties. Polymers are a great mechanism by which to hold the particles in place so they can you can see the function that they And so when you're putting these two things together, you still have a lot of choices to make. You can pick their composition, so the relative amounts of the two. I'm going to talk about the interaction between the polymer and the particle. That will be very important as we talk about dynamics. And these systems are rarely at thermodynamic equilibrium. So some of the disparity in the literature is very easily assigned to difference in processing methods. So, you know, once nanoparticles get agglomerated, they don't like to get unagglomerated. So the processing pathways are very important when you start to compare different sets. And if the particles are anisotropic, then you get to talk about nanoparticle orientation as well. So it's a very versatile class of materials. And I just want to highlight that nanocomposites are both historic and futuristic. Probably the most common historical nanocomposite are car tires. From the very early days of even natural rubber, adding carbon black was a mechanism by which to make them tougher. And carbon black, the smallest particles in carbon black are actually on the nanoscale. But this schematic is from a recent perspective or review in macromolecules that Sanat, Brian, and Rich and I wrote together. And you can see that it kind of just, you know, there are different sorts of cores, different sorts of functionality, different sorts of polymers you can compare, you can partner it with, and then the very outer circle are just a whole variety of different potential applications. So really, nanocomposites have been with us for a long time, and they will continue to be. Historically, it's a lot of you mix something up and then you go measure it. But hopefully we're going to bring a little more understanding of this moving forward. Where I think that the interesting science is really in the dynamics. And so you have things moving on a variety of different length scales, and this impacts both the properties and the processing. So with respect to properties, if you're looking at gas permeability through a nanocomposite, the segmental length relaxations are very important. So these would be glassy polymers, and you'd want to think about how they pack and how they might move near a particle. And so this is just an example that the permeability and selectivity can both increase with increasing nanoparticle concentration, right? But this is all local, very local sort of segmental dynamics. Nanocomposites are also being formed.
Karen, can you just speak to that a little bit? Are you making voids around the particles and it's going through the voids? What's going on there?
Yeah, so the chain packing is not as efficient up against a hard surface. So there's a little bit extra free volume. And again, it's very sensitive to that particle polymer interface. So if it's strongly absorbing, less free volume. Chain rigidity, that matters too. This is an example of dimensional stability if you were going to do imprinting to make nanoscale features. If there's nanoparticles in there, you can see this is the unannealed sample, this is the annealed sample. And if there are no nanoparticles there, the whole thing is just flattened out. And if the nanoparticles are there, you maintain the topography, right? So this is a flow, maintaining that shape during the fabrication. And then this is an example where there's a nanocomposite underneath a silica layer. And if that silica layer cracks, the fluorescent particles will migrate to that surface. And that might be good for something. It's also very important for processing. So how far particles move during the processing will indicate whether or not they actually bump into one another. And once they bump into each other, they're likely to agglomerate. So for injection molding, as you increase the particle concentration here, you're getting much more viscous system, and that will impact its ability to fill fine parts. This is very important for the automobile industry. Another very popular composite is nylon with clay, and that has really replaced a lot of metal parts, under the hood metal parts, with nanocomposites because they have better high temperature properties. And that lightweights the car and saves fuel. but you have to be able to injection mold into very intricate pieces. And this is an example of how.
Wait, I'm confused. So this says, is that G prime or G double prime?
Oh, that's G prime.
But you were talking about viscosity.
Sorry, slip. Yeah, so this is, viscosity will go up as well. But again, this is just to highlight the fact that as you add in particles, you're going to increase the resistance to flow, and that's going to have processing implications.
And so it's like the more stiff, the higher the modulus, then the less it fills those intricate. You want the low modulus for the intricate features?
Yeah.
But then, oh, so then the application is, but then what's that's when you're filling at high temperature. But then right? This is data for high temperature?
Yeah, this is high temperature data. This is melt data.
Okay, so then it can crystallize and become rigid and have good mechanical. Okay, so just when you're filling it, you want it to be, low, small.
Yeah. You want it more like honey and less like toothpaste.
Okay. Got it.
Yeah, and then if we think about nanoparticles diffusing in the system and how far they can move over the course of high temperature processing, they might stay dispersed or they might bump into one another and agglomerate. And so people know that this happens, but the fundamental understanding of it is still limited. So this is why dynamics is important. So if we just go back to what we know, certainly polymer diffusion is well described by the reptation model. So it's this idea that the polymer is constrained laterally. So the polymer here can't move left or right on either side of this green tube as easily as it can wiggle forward. And this is the tube is defined by the other entanglements and by the entanglements within the system. And so the polymer kind of has to wiggle its way out of the tube. And so we can approximate these entanglements with these cross marks. And the polymer chain has to wiggle its way through. Anyway, this is a well-established model. And the reptation model goes as this D naught, which has the frictional coefficient and the temperature dependence in it to the molecular weight to the -2 power. This is how polymers move in a high molecular weight, well-entangled polymer melt, so the absence of any solvent. And so just to remind you, the length scales that are involved in polymer reptation, the tube diameter is only a few nanometers. In polystyrene, it's 7. The end-to-end for reasonably high molecular weight polystyrene, the end-to-end distance in polystyrene is about 35 nanometers, and you have a diffusion coefficient 10 to the -14. But these are nanoscale. So the question that we've asked for over a decade now is how polymer diffusion can be impacted by nanoparticles that are on the same length scale. And so we've looked at spherical particles, we've looked at cylindrical carbon nanotubes and nanowire sorts of particles, but you could see that these particles are on the same sort of length scale as this reptation model. Now, looking at polymer diffusion inside nanocomposites is inherently complex because if the particles are, randomly placed, the intraparticle distance is not homogeneous. Sometimes they're a little closer, sometimes they're a little further apart, and this has implications for the polymer diffusion. So, we've also looked at polymer diffusion inside rigid wall confinement. These are very well-defined geometries, a thin film with symmetric confinement and then cylindrical confinement. And so just to the students who are out there, this is a fine example of putting together a seminar with disregard to the historical sequence. So we did a whole bunch of experiments over here. And more recently, we've done simulations over here. But the thread of the story is much, I think it'll hold together better if I throw history out the window and I just tell you the story in the order that makes sense. So we're going to start here. So we're going to look at polymer conformations and polymer diffusion inside symmetric confinement. So simulations in both thin films and cylinders, and then we have one set of experiments in anodized aluminum oxide cylindrical pores. And again, we did the experiments before we did the simulations. But let's start with the simulations. So we're confining polymers, you know, with infinitely long cylinders or infinitely wide thin films. You can see that we're picking, these particular simulations show that we're using, the gray beads are the rigid wall. We're not using a flat wall, we're using a glassy bead, we're using a wall that's made out of glassy beads. And this is to prevent crystallization at the smooth surfaces. And we're defining a confinement parameter, which is the 2Rg is the length scale of the polymer, so that'll depend on molecular weight, divided by the thickness of the film. And then in the case of cylinders, it's the radius of gyration of the polymer normalized by the effective radius of this cylinder. A range of molecular weights, the entanglement, well, beads, sorry, a range of bead, number of beads per chain, and the entanglement beads is just 50. And a range of thicknesses and radiuses so that we have a wide range of confinement from like 0 to about 10 in both geometries. All right, so these were the simulations that James Presley did, and he was co-advised by Rob Riegelman at Penn. Okay, so the first thing we look at is the chain conformation. This has been, it should be conformations, and that these deviate from the bulk. And they deviate differently depending on whether it is in the confined direction or the unconfined direction. And this should not be surprising when you think about it, that, you know, if in this direction, things are going to be a little squashed. So in the confined direction, things are going to be squashed. And what's interesting is if we plot the radius of gyration relative to the bulk as a function of this confinement parameter, the cylinders and the thin films have the same level of deviation from the bulk. And then that's the confined direction. And then in the unconfined direction, the thin films are a little less deviated than the cylinders, because, you know, the cylinders are curving around and are making that, are further distorting the chain conformation from the bulk. Okay. We also looked at the entanglements because, like I said, polymer diffusion is associated with the entanglement density of the network. And so you can see here, this is the entanglements per chain as a function of these two parameters. The thin films and cylinders are on the same plot. Green is always cylinders. And these are different molecular weights, right? And so the dashed line tells us what it is in the bulk. And as we go to a thinner film or a smaller radius, that these tilt downward. Right? And if we look at this molecular weight of 100 beads, that this reduction in the number of entanglements is more significant in the cylinders than in the thin film. And the reason there's less entanglements is really because of this idea that the random walk has to reflect off an impermeable wall. So if this is our polymer chain and it's taking its random walk, and then we insert a wall there, the random walk is reflected back into the polymer melt. And because these red segments are in the polymer melt instead of inside the wall, it displaces other polymers. And so there are fewer entanglements with other chains. And so it's, you know, there are actually equations that people have developed to explain this quantitatively. All right, so this is a nice comparison between the cylinders and the thin films. Fewer entanglements with further confinement, and this drop-off is more dramatic at higher molecular weights. What was surprising to us is that we could write a very simple volume fraction expression for this. So the curves that are on this plot are simply given by this. So this, these simple volume fraction expressions divide the confined geometry into two parts. There is some regular material and some material with no entanglements at all. So instead of thinking about it as a whole bunch of shades of gray, we're just going black and white. Regular number of entanglements, no entanglements. And so the fitting parameter for these expressions to fit the data is just this thickness. And so the thickness is higher for the cylinders. So at a fixed amount of fixed dimensionality here, there are more, sorry, this is thinner in the film and larger in the cylinders. And that's consistent with, you know, the bigger drop. But they both depend on molecular weight. And so it's a stronger molecular weight dependence for the cylinder than for the thin film. Okay. So a little bit about chain conformations, a little bit about chain entanglements, but we're really after the diffusion. And so because we're losing entanglements, the diffusion is faster.
Actually, I just have no intuition for understanding this dependence on the chain length. I guess I would have thought that it doesn't matter very much beyond
so,
like
yeah, so just
like some length scale in a long
right.
polymer, right?
Yeah, so the amount of folding back on yourself will be more dramatic if you are a higher molecular weight polymer. And
is that because you don't count self-entanglements as entanglements?
oh, correct. Yeah, self-entanglements do not limit diffusion. So the mass density is the same, but by reflecting off of this wall, you are eliminating entanglements with other chains, and so that will have a molecular weight dependence. It's not as strong as I would have thought. It's molecular weight to the 0.2 for thin films and closer to 0.5 for cylinders. Okay. So you can see I've erased some of the obstacles here. And so if we have fewer entanglements, the diffusion should be faster. So as we get more confined, we can see this normalized diffusion coefficient increase. And it increases to a greater extent for higher molecular weights, because a higher molecular weight chain up against a wall is going to have fewer entanglements with other chains. Okay, so now I'm just going to insert the experiment, and the experiment is what we did first. So we used a method called elastic recoil detection. And so anodized aluminum oxide are alumina templates that have very well-defined cylindrical pores, and we filled them up with polystyrene. And then we put a thin layer of deuterated polymer styrene on top, and we let that deuterated polymer diffuse in. And elastic recoil detection can separate out deuterium and hydrogen. And so now this is a concentration profile from the free surface into the depth of the pore for the deuterium. So this green curve is all the deuterated polymer. Now you'll first see that there's a surface peak. So there's a little bit of polystyrene that just stays on the surface because it's hard to get from on top of the oxide into the pore. But the stuff that gets into the pore goes like this. That's the red curve. And then you sum the red and blue curve to get the green. And without going into a whole lot of experimental results, I'll just share one. So we looked at different molecular weights and different pore sizes, but here's an example for the diffusion coefficient in the bulk is 4.8 times 10 to the minus 15 centimeters squared per second. And then in the confined system, an 18 nanometer hole, the diffusion coefficient is 42% higher. So things are getting faster when you diffuse into pores. And so this is what we went after then in the simulations. And we kind of saw that, but we saw something else that was quite interesting. So again, this is the normalized diffusion coefficient. So diffusion in the confined system normalized by the bulk as a function of the radius of the pore. And as you get more confined, it's increasing, right? So it's hard to see all the different shapes, right? But sometimes it increases a lot. If it's 500, it increases just a little bit. But then there's the surprise. Then it rolls over and gets slower. So the increase in diffusion coefficient we can understand because it's disentangling. Disentangled things don't diffuse faster. But this rolling over was a puzzle until we appreciated what was happening on a morphology side, in terms of morphology. So when the pore got very, very small, the change segregated. And so now you can imagine that for this orange chain and this purple chain to exchange, they have to become very elongated and wiggle past one another. It's a huge entropic barrier for diffusion once you get this small in radius and you have this segregation of chains. And what's plotted here on the right is this confinement parameter as a function of pore radius. And this is the lines on here are from work by Lee. So describing the difference between weak and strong, and but these are both still dispersed. And then this curve here has this dependence, where this is the Kuhn step length. This is the density of polymer. So this really just goes as R squared, where R is this confinement parameter. And you can see that curve here. The symbols that are open are the symbols that in our simulations we found the chains to be segregated. So if you look closely at this, these open symbols are the segregated ones. And so now we understand that this is the loss of, this increase in diffusion coefficient is the loss of entanglement until it gets so confined that it segregates. And that doesn't happen in the thin films. Because in the thin films, even if you're very, very confined, we see a little bit of tending towards segregation, but still the entropic penalty isn't the same because they can kind of do-si-do around one another. Whereas in the cylinder, the entropic barrier is much higher for the polymers to have to pass one another. So that's what we learned by looking at confinement, rigid wall confinement in thin films or in cylinders.
And is it something like a blob length? I mean, you get down to a blob and then that's when the segregation happens?
I don't think I've thought about it in terms of blobs. Yeah, I haven't taken our numbers and converted them to see where they would impact on a blob size. Yeah. Okay. Well, let's try and take the next step towards polymer nanocomposites by starting to introduce some nanoparticles. Okay. Now, the simulations on this could be very, very expensive if we put in particles everywhere. Plus, if, like I said, if we have randomly placed particles, it's inherently heterogeneous because sometimes the particles are closer together and sometimes they're further apart. So in an effort to simplify things, we did this monolayer of nanoparticles. So we can look at the chain conformations and the chain scale dynamics, their diffusion in this volume. And again, the simulations came second, the experiments came first. But here we go. I'm going to tell you about the simulations first. All right, so we decided to simulate a monolayer because we were looking for some insight on center of mass diffusion in nanocomposites. All right, so it turns out there's this, we can't define the confinement parameter the same way we did with rigid confinement. So instead, in a nanocomposite, we've defined confinement by this interparticle distance. So from the surface of one particle to the next, relative to the raised to gyration, or 2 times the raised to gyration of the polymer. All right, so this is our confinement parameter. And in this particular set of simulations, we had 2 different chain lengths, and we had 3 different particle sizes, 3.5, 7, and 14, and we varied their spacings. Actually, I think this is another typo. And we varied their spacings so that we have a range of interparticle, we have a range of this confinement, ID over 2RG. Okay, so just like we did with the rigid confinement, we're going to look at chain conformation, and then we're going to look at chain dynamics, center of mass dynamics. Okay, so these are color maps, where we're either looking at the XY plane, which is the long side here, or we're looking at a cut through the center. So either the XY plot plane or the XZ plane. Okay, and the blue data, again, we're looking at the raised to gyration perpendicular to the surface versus what it is in the bulk. And the blue indicates that things are a little flattened. And this is with an athermal surface. So the polymer interaction is the same as the polymer particle interaction. And so even in that case, the chains are a little bit squashed onto the particle surface. Right? And what's interesting is the thickness of this compression is independent of the interparticle distance. Right? It's really just about the particle. And that's more evident here when we take these line traces across and then plot the raised to gyration perpendicular to the surface relative to the bulk. And up against the wall, it is always the same, about 0.75. Right? And then when the particles are far enough apart, it's compressed at the wall, and then it goes back to the bulk level, and then it goes compressed to the next wall. So that would be this one, where there's some compression here, then it's like the bulk, and then it's back to compressed on the second particle.
Could you just clarify, is this RG calculated like from an individual polymer, or is it like monomer to monomer, and how are you calculating RG?
So this is the radius of gyration of an entire polymer chain. These polymers are only 50 beads long. And what I forgot to mention was that where do we put them on this distance between the 2 particles? And that we do from the center of mass of the chain. So you look at a chain, you calculate its center of mass, you get its RG relative to the surface. Okay, and then what's interesting is if we look at this one, the most confined, so the particles are really close to one another. And for guidance here, we put on 2 additional curves. And these are kind of, 2 extremes. The dashed curve here is how much compression there would be if you had equal contribution from both particles. So as you go from one particle to the next, that you're feeling the compression from both equally. And then the dotted line here is if you only feel the compression for whichever particle you're closest to. And it turns out that the simulations give us data that's kind of in between the two. And the solid curves here are what you would get for a random walk inside this geometry, which is good news, which means not everyone's going to have to go through and do this simulation for different detailed cases again. You can just do a Gaussian walk inside the geometry and you get the same sort of compression. Okay, so probably one of the most interesting things we found here was, you know, when you want to compare different nanocomposite systems, you get to pick a lot of different variables. And if you want to think about the chain conformation, it's important to think about both the polymer molecular weight and the size of the particle. It's not just the size of the particle that matters. It's how big is the particle relative to the size of the polymer chain. And that's made clear here. So this is, again, the normalized raised to gyration perpendicular to the particle as a function of distance from the surface. And so, Seth, these points here that are they all look like they're inside the particle. That's because if you have a polymer chain, its center of mass mathematically can be inside the particle. All right, so that's what these are over here. But the color scheme is complicated, but let me just try and walk through this. So there are 2 different molecular weights, 3 different particle sizes, and 2 different ID over 2RG values, right? But the things that line up and have quantitative agreement with one another are the systems that have the same nanoparticle to polymer size ratio. So the different shapes, triangles and circles here, indicate 2 different values of nanoparticle to RG. And so that the relative sizes of those 2 objects tells us how much the chain conformation is going to be distorted near the particle. And these distortions, I mean, once you get up to this very large nanoparticle relative to the RG of 2, you know, we have a distortion of about 50%. It's compressed by 50%. And this distortion goes out, you know, it's all this chain conformation distortion only persists out about an RG. Okay, that's important because what we're going to see is the polymer diffusion, the distortion or the disruption in polymer diffusion is much longer scale than the chain conformation. Okay, so on to polymer diffusion. So because we have this very
intuition on this, why you have a compression, I almost would expect the opposite, that because of entropy, it would, I don't know, like be less compressed. I don't know, avoid the surface or something.
Yeah, so interesting, I glossed over this, but when the nanoparticle is smaller than its raised to gyration, you do get a little bit of an increase here before it decreases. Yeah, and then these are the particle, all these.
Is the polymer wrapping around is that why it's getting denser? Because it kind of hugs the nanoparticle? It conforms to the surface?
It's not getting denser, just like when the chain conformation was distorted at the wall of the thin film, it's not getting denser. The bead density is the same in the simulations. It's just that it's taking a different random walk. It's taking a flatter random walk. And then, Seth, these the shadowy particle points correspond to the chains that are kind of wrapping around a particle, because then their center of mass is interior. Yeah. Okay. Okay, but you know, the focus of doing all of this was the diffusion. So now that we have this monolayer, we can look at the diffusion at different distances from this monolayer. And so we look at the dynamics of individual beads in the melt, and we look at a whole trajectory of one bead, and we see what is its average height, its average Z distance above the monolayer. And we assign it that Z value, or its average Z value over the course of its trajectory. And then we can think of these different bands, right? 2 RG away, well, inside the layer is the dark purple, and then different distances away from the monolayer. Okay. So we can look at diffusion coefficient as a function of distance from the monolayer. Okay. So we see that far away from the nanoparticles, it's just about normal. So this is, again, the diffusion coefficient in the Z direction relative to the bulk. The diffusion coefficient in the Z direction in the bulk. So very far away, it's just about what you'd expect for the bulk. And as you go towards the monolayer, the diffusion gets slower. And it gets more depressed. There's a more significant change when the particles are very close together, right? When we're in a very tight packing. And then once you're inside the layer, things move a little faster than they do in bulk. We'll talk more about that in a moment. But the big news here is that closer to the nanoparticles, things are slower. Things are more slower for higher nanoparticle densities. And then the thing that is surprising, remember the RG, the change in the chain conformation, only lasted about 1 RG. And here the distortion in the diffusion coefficient is out at least 4 or 5 RG. And this depression, you know, 30% or whatever, 10, 15% is significant. Right? It's a monolayer. It's like, I think of it as like Princess and the Pea, right? There's just one layer of nanoparticles, and polymers that are 6 RG away are still slower than they should be. And so the fundamental physics behind this, I still struggle with. I believe, you know, the results are robust, but like how the distortion of the chains down here can impact what's happening mostly up here. I still have a little difficulty with it. It's much longer range than I would have expected. So we looked at some Van Hove calculations from this. So this is just to remind people what Van Hove is. So you have a bead at time 0, and then you measure its probability of getting a certain distance away at a later time. So we're doing diffusion just in the Z direction because that's the symmetry of our system. So it's some delta T or delta Z away. And so in the bulk, these data are here for the bulk, for different times, short, longer, longest time, you can see that, you know, at infinitely short times, is going to be a delta function around 0. And then as longer and longer time, you're going to have this Gaussian spread. You can look at the width, the half width of this Gaussian, and plot that half width as a function of the time delay, and you get this parallel dependence, and this is how we can extract out the diffusion coefficient. There's your reminder. Now, if we do this for a layer of polymer that is right next to the particles, we see an anisotropy. So the raw data straight out of the simulation is the dashed line, right, with this dip here. And so originally we thought, okay, well, of course there's a dip. because the orange polymer here diffusing in here, there's a lot less space for it to go. So of course there's going to be this, this depression here, just because of the volume. But then we corrected the data and normalized it for the amount of available volume, right? So 100% available over here, 100% available to the left of the particles, but inside these particles, you can do the math and figure out how much available space there is. And still, it's subtle, but that solid curve, the corrected data, is also anisotropic. And so this gives us an opportunity then to fit Gaussians to the left and to the right. So if we look at the Gaussian going into the particles as opposed to out of the particles, we can get two different diffusion coefficients going in and coming out. And so that's these data. So we have the diffusion coefficient. It's just about what you'd expect for the bulk if you're going away from the nanoparticles. And if you're going towards the nanoparticles, things are slower. And again, this is, and it gets more significant as you go to more confined systems. And we're using here this, parameter, ID over 2RG. So just to wrap up the chain diffusion from the simulations, in confinement, more confined, because you're decreasing the number of entanglements, you get faster diffusion until you've confined things so much in the cylinders that they become segregated, and then things get much slower. And it's really quite different in the nanocomposites. Even with the monolayer, we can see that there's a long-range distortion of or a long-range effect of the nanoparticles on polymer diffusion. The nanoparticles are slowing down polymer diffusion, even far away from the particles. And that overall there's this anisotropy, right? So moving towards the particles is a lot slower than moving away from the particles. So what I'm going to show you next are experimental results over half a dozen papers, maybe 8 papers, showing that this normalized diffusion coefficient rolls over like this as a function of ID over 2RG. So this is a whole bunch of data. Let me tell you how we get that data. So again, elastic recoil detection can tell the difference between deuterated polymer and regular polymer. So you put a little deuterated polymer on top of a nanocomposite, you can watch that deuterated polymer diffuse in and measure its concentration profile. This is actually a lot easier to do in the nanocomposites than it was in the AAO templates. Much better signal to noise. So this diffusion coefficient here, the only fitting parameter you have is the diffusion coefficient. H is the initial thickness of the tracer layer, and T is time. And we experimentally measure this concentration profile as a function of X, depth into the sample. And so in our first set of experiments with spherical particles, we did this with nanotubes first, but I'm only going to show you the spherical particles today. We can see that the diffusion coefficient without nanoparticles and then with more and more nanoparticles decreases, and for all these different molecular weights. So polymers are moving slower. Even when the concentration of nanoparticles is quite low, we're still getting a significant drop in the diffusion coefficient. And by the time we're out to 50% nanoparticle concentration or so, we've dropped by an order of magnitude. Right. And this is just highlighting that we have a processing trick that allows us to get well-dispersed particles. Even though these are athermal particles, and thermodynamically, they want to find one another and stick. But kinetically, we've kept them apart. And so this was the first time we collapsed data. This is the normalized diffusion coefficient as a function of the interparticle distance normalized by 2RG. And, you know, we didn't redo that data point. And the error bars are from duplicate experiments. And so this is really remarkable collapse for a challenging experiment. And so the magnitude of the decrease is, you know, almost an order of magnitude when we have a very small ID over 2RG. And when we're at an ID over 2RG of 3, we're still 25% below, or nearly 30% below the bulk diffusion coefficient that's expected. So very much princess and the pea. You know, here the particles are 3 times the distance away from what RG is, and it's still making a substantial reduction in the diffusion or the center of mass chain dynamics. And then many, many experiments later, we can get a whole, this is a very powerful way of looking at this decrease in diffusion coefficient. What is captured in this summary plot are the bare particles, and then particles with low grafting density and particles with high grafting density. And the only difference, the only correction that was made to get all this on one plot is that we used an effective interparticle distance, meaning we're taking into account, if you see the dashed blue circles here, we know the matrix polymer can only get so far into a grafted brush. And those calculations were done using self-consistent mean field theory. So we know how deep they can get in. And so everything else is impenetrable. So the D effective is bigger than the actual particle itself, but that's the impenetrable part. And so big drop in diffusion coefficient as much as a factor of 10. And then way out here, ID over 2RG of 14, and we're still not quite back to bulk. And that, I think, is the puzzling piece, that so few particles can still somehow slow the polymer diffusion down. These are all in athermal systems at 170 degrees C, and we have a weakly absorbing material that also showed the same trend. So, I'm going to skip the stuff about cylinders because I just want to say quickly something about nanoparticle diffusion. So yeah, we cannot assume, the other caveat on the polymer diffusion results is that the particles are big enough and the temperatures we used were such that the particles diffused at least 100 times slower than the polymer. So the particles are effectively immobile to have that normalized diffusion coefficient over as a function of ID over 2RG, to have that collapse. Okay, now let's work with a different system where the particles are a little smaller and we can get them to move in the polymer. And we wait longer. So now we're using Rutherford backscattering. It's the same ion beam, but we look at a different signal coming off, helium in, and then we look at the helium come off, and it can give us a concentration profile now of the silica rather than the deuterium as a function of depth. Okay, so at time 0, we just have the nanocomposite at the top. This is not drawn to scale. The matrix is much, much thicker. And over time, we can watch the diffusion of the particles in. Again, one fitting parameter for the diffusion coefficient of the particles. In this case, we're using an attractive system where the nitrogen in the poly 2-vinyl pyridine likes to stick to the OH groups. And it's well established that there's an attractive bound layer on particles when you have this attractive interaction. And that's been shown by segmental dynamics at the surface. And if we compare this to, so I'll remind you about Stokes-Einstein. So Stokes-Einstein, Stokes-Einstein predicts the diffusion coefficient of a particle based on the viscosity of the system and the size of the particle. All right, so we measure the viscosity of our polymer. And one of the underlying assumptions of Stokes-Einstein is that the fluid is interacting with the particle, or bombarding the particle in a Brownian way. Okay, so these green dots is not how I normally think of a polymer, particularly one that is adsorbed to the surface. Okay, so if we compare our diffusion coefficients relative to that prediction from the Stokes-Einstein, we see that our particles are moving a little slower. And this is pretty easy to understand because we know we have an adsorbed layer. So we can calculate from the diffusion coefficient what the effective size is, right? And then we also have from DLS. Now DLS is in a solvent, so the chain will be much more swollen. This is in the melt state from the diffusion coefficient. And we see that this increases with molecular weight, which makes sense because this is now the thickness of this adsorbed layer, and the thickness of the adsorbed layer in the melt is increasing as molecular weight to the 1/2. So it's increasing the same way as Rg would increase with molecular weight. And so, well, there's another slide that apparently I've hidden unless I've put it out of order. Okay, well, like I said, you guys are the maiden voyage of this talk. One of the things that's difficult about doing that nanoparticle diffusion experiment is if the particles are athermal, and you have to do a very long anneal, they will agglomerate. Because to have enough signal, we have to put in like at least 5 or 8% particles. So we've gone to single particle tracking. And in the melt state, so, single particle tracking is, we're using quantum dots. There's a lot of math involved to find the center of those bright spots, and those bright spots are larger than the particle, but we can still very precisely determine the center of those particles as a function of time. The chemistry we're looking here, and what we were really excited to do, was to look at both sticky and non-sticky quantum dots. Again, the sticky ones, yeah, we'll have a polymer adsorbed and that will prevent agglomeration, but for the non-sticky ones, there's really no other way to do this experiment with non-sticky particles to get their diffusion. So from the two-dimensional trajectories, this is nearly 2,000 tracks, all starting arbitrarily at 0, 0. You can see there's these are random. There's no bias here. They're not drifting. So this is a good data set. And this is how we identify the center of the peak, the center of the intensity. Okay, single particle tracking. And then we can calculate the mean square displacement from all of those tracks. The colors are individual tracks, and then the black line is the average, the ensemble averaged. And then out here at like 1/2 to 1 second, we have diffusive behavior, and this is how we extract the diffusion coefficient from the single particle tracking experiment. Okay, now we have one set of particles, and we have 2 sets of particles, sticky is in red, non-sticky is in black, and 5 different molecular weights. And we see that the sticky particles are slower. And as we saw in the polymer melt before, the sticky particle, the effective radius or size of these is increasing with molecular weight, power law to 1/2. But the new data is that the non-sticky ones are not. So it's a non-result. They're behaving just like Stokes-Einstein, and that we can see here. So this is the single particle tracking normalized by straight up Stokes-Einstein. And in this case, the particles are the same as the core particle size, the non-sticky ones. And then the sticky ones, we have a absorbed polymer layer, which scales, which is the same size as RG. So I was worried about not having enough to say. I apparently had plenty to say. Thank you very much for your patience. Today we talked about polymer and nanoparticle center of mass diffusion. We did simulations and experiments both in rigid confinement and in the presence of nanoparticles. And there again is the website at the bottom. If you want to read any of the papers in more detail, I'd be happy to take any questions.
Thank you, Karen.
You're welcome.
Yeah. I guess I'll open it up for questions. Does anyone have any questions? Seth?
I guess I have one more, yes.
I'll pay you later, Seth, for being attentive and asking questions.
So, you know, you had said at one point that the diffusion going in and going out were different. And so then, I guess, you know, that means, but the fluxes of going in and coming out have to be the same because of equilibrium. So it's like something about the density has to be different, has to be a density gradient. You can't have like, there's got to be like some law of mass action kind of thing, right? Where the in and out has to, the viscosity has to kind of be the same for each direction. There has to be a.
Well, I will not go as far as saying is the viscosity is the same in, throughout the system, but the mass density is. And so moving towards the particles, you just have to wait. There's a much bigger entropic penalty because to get in between the particles, you kind of have to come out of your random walk and like get in there. And that's just a larger entropic barrier than going the other direction.
Yeah. Yeah, but I mean, the rate of particles coming in has to be the rate of particles coming out. Otherwise there'd be accumulation.
Right.
So then I'm saying, so then if like, you know, if it's harder to get in than to get out, then there must be more trying to get in than are trying to get out or something, you know, so that flux balances, you know what I'm saying?
Yeah. So the flux is balanced, and I'm trying to remember how we explained this in the paper. I don't know if I'm going to be able to find the words to do that today, but it's yeah, I don't know. I'm sorry, I can't think how to explain that there is no flux buildup.
Yeah, no, because in equilibrium you can't have that. So steady state you can't. You got to have a balance, and then if the in and out rates are different, then it's got to be the densities, you know, or the temp, you know, the densities are different, though, or
well, certainly the densities are different because if you in the monolayer, a bunch of space is taken up by the particles.
Yeah, but it's
but we've corrected for that.
Yeah. Anyway, it's
okay.
There's some balance thing that has to happen. I don't see it in my. It's got to do like with the temp frequencies, right? It's got to be if it's hard to get in, then you've got to be trying more often, and so maybe just because of the geometry, like if it's spherical, there's more outside than inside, you know. And so there's more attempts coming in than attempts going out. And there's got to be some equilibrium demands. There has to be some, you know, compensation. That's the word I'm looking for. Anyway, all right. That was the question.
Do you mind if I ask a quick question?
Sure.
Would you mind just describing one more time how exactly you're measuring the depths of these polymers into your little slots experimentally?
Sure.
Yeah, I just was not familiar with the method. So there's like some deuterated things. And so what what exactly, like what wavelengths and stuff are you detecting?
So elastic recoil detection is an ion beam method. So it's helium in, and then it forward recoils the deuterium and the hydrogen. And so the helium loses energy as it travels into the film, and then the hydrogen and the deuterium lose energy on the way out. And so you look at the energy, first of all, you look at the energy of the helium, you look at the energy of the hydrogen and deuterium that come out in ERD. So there's different variations. So notice this is a glancing angle of helium, and then it kicks out, the stopper film blocks the helium, and now you're detecting the energy of the hydrogen and the deuterium. And that energy can be converted to depth if you know the composition. So it's all nuclear. So it's just like when a helium ion passes past carbon, the carbon atom, it's going to lose a little energy. And so if you know the well, actually, we just do it with a polystyrene layer where we know it's all polystyrene. So there's different ways you can calibrate the energy. But the energy tells you how deep into the sample the hydrogen and deuterium were. Okay. We don't look at the hydrogen signal because it's too close to the carbon signal. So we look at the deuterium signal. So on this axis, this is just number of counts, the number of deuteriums that get to the detector effectively. And then this is the energy of the deuterium that gets to the detector. So the deuterium that comes off the surface is the highest energy, and the deuterium that was buried inside will come off with a lower energy. And so ERD is the uncommon version of this. The more common version is RBS, Rutherford backscattering. And that geometry, well, let me just go show you that geometry, because that's what we use for the particles. Oops, so apparently, well, oh yeah, little tiny schematic. RBS is backscatter, so helium perpendicular to the film. Helium loses energy on the way in, interacts with the silicon, loses energy there like a billiard ball, and then comes back out of the surface with a lower energy. And so here, again, the helium that comes off, you're detecting its energy, and you convert that energy to a depth because it tells you how deep into the sample it had to go and what atom it interacted with at that depth.
Okay, that's really cool. Thanks.
It's a very cool method. It was all the rage, I would say, in the 70s and 80s when they were doing ion implantation into silicon for devices. And there were a lot at universities. Our ion beam is now mothballed, sadly. These are very complex. It was $1 million 30 years ago, and it's just a hunkin' big accelerator to get these. The helium is at like 3 MeV and focused. Sandia probably has the best set of ion beam characterization tools right now. Sandia National Lab.
Well, cool. Thank you very much.
Oh, you're
Very
welcome.
interesting work. Thanks for sharing it.
Sure.
Yeah, I'm still extremely puzzled by this long length scale interaction that's happening. I mean, do you have any some sort of intuition about maybe what is going on, or ideas for what rock you'll look under next?
Yeah, my intuition can get us out to like 3 RG. Because like the way you're entangled will impact how the next one's entangled, and your conformation is gonna be different if you're near a particle. But I don't have anything that can get us out to 10 RG and still be somehow slower.
In your simulations, have you been able to look at sort of other conformational parameters besides the radius of gyration to get some idea of something beyond that? Or like
we haven't.
Because I mean, if you have simulations, that's all. I mean, exactly what's the
Yeah.
structure.
So the simulations with the monolayer particles were barely entangled, which further surprises that there's really any decrease at all. But we tried to do much larger chains, but it's just too slow. Now, I think if, again, the same person who, that student was doing simulations on the side, that was like his weekend habit. But you know, if Rob Riegelman put his mind to it and all his computational power behind it, he might be able to do higher molecular weight chains, and that I think would be important for figuring this out.
I'm going to run off, Karen. Thanks a lot. That was really
My
nice.
pleasure.
I enjoyed it. So most of our seminars are very like bio or, you know, active matter and stuff. And so it was good to see like an old school colloid polymer. I haven't, you know, it was very refreshing for me. So thanks a lot.
Good.
And then I just downloaded your paper on the single particle. So I'm teaching, that's exactly the lab I'm teaching online this week, is single particle tracking and in colloids. And normally we'd have them come in the lab and record it on a microscope. But now I give a pre-recorded, just looks just like what you showed, you know, and then you trace 100 trajectories and do the MSDs and stuff and do an analysis. That's exactly the lab I'm teaching this week.
There you go.
So I'll post your paper as an example of current research.
Well, thanks very much. Thanks.
See you.
See you. Bye.
Bye.
All right, well, if there are no further questions, let's thank Karen again for the really clear and nice talk, and I'll end this seminar then.
All right.
Thank you.
Thank you very much.
All right.